Okay, so we've talked about how to find an inverse function given any function. And actually we used a linear equation as an example, but the truth is that that procedure of flipping the input and the output variable will work for any function from now until the end of Algebra 2 and beyond. But now we want to talk about what that looks like graphically. That might seem like just kind of a random thing to throw in, except for the fact that inverse functions have a unique graphical significance. So let's take a look at our example over here, which happens to be the function and the inverse function that we found in topic 1. Notice that, so we have y equals 3x plus 2, which was our original function, and then we have y equals 1/3 x minus 2/3, which was our inverse function. Now to the left of that, I've put two symbols, or two function notation symbols, that I want to explain what they mean. The f of x we already know just means that this is a function. In fact, it means that it's a function we have named f. Now in the second row, it looks almost the same, except we have this tiny little -1. It's almost like a power, like if you have x squared, I write that 2 really small. The f with a little -1 is written in the same way. Now it doesn't mean the same thing, but I just want you to know that's what we would call a superscript. That is read as the inverse of f. So that little -1 symbol is symbolic for inverse. Just want to make sure that you're aware of that, so if you see it turn up anywhere, you'll be able to read that notation and know what it means. So now that we have an f and an f inverse, or a function and an inverse of that function, let's see what happens if we graph it on this xy plane on the right. So first equation, thinking about this in terms of y equals mx plus b, remember the first thing I do to graph is I find the y-intercept, which is 2. And I draw a point. Then I find the slope, which in this case it's the coefficient of x, so in this case it's 3. That means it's rise over run. 3 over 1. Go up 3, 1, 2, 3, and over 1. And that is all I need to do. Just connect the dots. Whoa, that's not a straight line. Let me see if I can do that better. Drawing diagonal lines on a computer for whatever reason is just counterintuitive. Okay, so there's my attempt. Next, I'm going to draw, using the similar color, my inverse function. So again, I go to the intercept. In this case, it's -2/3. So that's a little bit weird. It means it's not quite 1. It's 2/3 of the way to 1. And then I find the slope, which is 1/3. That means it's rise over run. That means we go up 1 and over 3. From 2/3, up 1 would be about here, and then over 1, 2, 3. And that would be right there. And then I take these points and I connect them. Now, I'm going to go back to this and try to make it a little bit clearer. As I graph these two functions, I want you to notice that they look kind of like mirror images of each other. And if that's kind of the initial reaction you had, that is a good mathematical operation. Specifically, if I put a mirror down right here, or if this was a piece of paper with maybe paint on it, and I folded it right along this dotted line, this line and this line would match up perfectly. So I have a diagonal line here, I have my function, and I have my inverse function. And it just so happens that they're mirror images of each other kind of along this diagonal line, which actually happens to be the line y equals x. And this is our interesting property of inverse functions, is that they always are mirror images along the line y equals x, no matter what kind of function we're dealing with, whether it's a line, whether it's a U-shaped graph or a V-shaped graph, or it could be a really crazy looking graph. It could just be like a bunch of wiggles. Even if the function looks like this, if we take a function and we find its inverse, it will always have mirror image symmetry along this line of y equals x. Now, that is mostly, in case you're wondering, why do I care about that? That's mostly just a little piece of information I want you to tuck away. So finding inverse functions, that's something we're going to be working with right away. And we'll graph some of them. We'll see how they relate to each other, just to make sure that you believe me that really all of them have mirror image symmetry. But for the most part, I want you to take that information, tuck it away, and we're going to bring it up again as we move forward in our learning different types of functions, ones that are a little bit more interesting and more complex than lines.